This is Aritra Chakraborty. Today I am going to discuss about the basic principles, EMF equation and voltage transformation ratio of single phase transformer. So now this is the first slide, that is the introduction about single phase transformer. A transformer can be defined as a static device, or you can say a transformer is a static electromagnetic device which transfer electrical energy from one circuit to another circuit, or which helps in transformation of electrical power in one circuit to electrical power of the same frequency in the another circuit. So when the power is transformed from one circuit to another circuit, then the frequencies remain constant. The voltage can be raised or lowered in a circuit, but with a proportional increase or decrease in the current ratings. That means when the voltage is increased, then the current is reduced. Now the next slide is the working principle of transformer. The main principle of operation of a transformer is mutual inductance between two circuits, which is linked by a common magnetic flux. A basic transformer consists of two coils. One is primary coil, another is secondary coils, and that are electrically separated and inductive, but are magnetically linked through a path of reluctance. So that means the two coils of a transformer are connected by a mutual inductance. So the working principle of the transformer can be understood from the figure below. So here you can see the working principle of transformer. So there are two coils, one is primary coil or primary winding, another is secondary winding, and these are two connected by the help of a magnetic core. So this magnetic core is made by a ferromagnetic material which has a greater permeability, and it is laminated. That means the thin chips, iron chips or iron plates are connected with each other to make the laminated core. So when the voltage is applied to the primary winding, there is a flux is produced in the core, that is phi, and which is linked with the secondary winding, and hence there is a EMF is induced in the secondary winding, and this flux then cut the primary winding also. So there is a self-induced EMF in the primary winding. So in the secondary winding there is a mutual induced EMF, and in the primary winding there is a self-induced EMF. And if we connect a load impedance with the secondary winding, then a load current will flow through the secondary winding. So that is the working principle of a single phase transformer. Now a mutual electromotive force is induced in the transformer from the alternating flux that is set up in the laminated core, which I have already told that due to the coil that is connected to a source of alternating voltage, most of the alternating flux developed by the coil is linked. That means the alternating flux, the maximum number of alternating flux is linked, and the minimum number of alternating flux is act as the leakage flux. Okay. So with the other coil, and thus produce the mutual induced electromotive force. Now the EMF equation of a single phase transformer. Let the N1 is the number of turns in the primary winding, N2 is the number of turns in the secondary winding, phi m is the maximum flux in the core in Weber, equals to Bm into A. So what is Bm? Bm is the flux density. That means flux in per unit area. That is the flux density. And A is the area of the core. So if we multiply Bm with A, we can find out the maximum flux in the core, that is phi m. And F is the frequency of the AC supply in Hertz. Now you can see here a sinusoidal wave. That means the flux which is produced in the magnetic core. So the maximum value of the flux is the phi m and the time period is t. So here you can see that if it is t by 2, it is also t by 2, and hence this total time period is t, then the maximum flux can be obtained at t by 4 second time, and that is the maximum flux. This is the maximum value of flux. Phi m stands for maximum flux. So as in the figure in the previous slide, the flux rises sinusoidally to its maximum value phi m from 0. You can see that it rises from 0. Flux rises from 0 to the maximum value. It reaches the maximum value in 1/4 of the cycle, so that is t by 4 second, where t is the time period of sine wave of the supply, so that is equals to 1 by f. That is the f means the frequency. So therefore the average rate of change of flux equals to phi m by t by 4. So the average rate of change of flux means the phi m is the maximum flux and t by 4 is the time when the maximum value of flux can be achieved. That phi m by and 1 by 4f, where t is the time period of sine wave of the supply, that is 1 by f. Okay, so average rate of change of flux, that is equals to 4f phi m in Weber per second. So now the induced EMF per turn equals to rate of change of flux per turn. We know from the Faraday's laws of electromotive induction, the EMF, induced EMF, equals to the rate of change of flux, that means Weber per second. So now therefore average EMF per turn 4f phi m. Now we know the form factor equals to the RMS value of and by average value. So average value is 4f phi m, therefore RMS value of EMF per turn equals to form factor into average EMF per turn. EMF per turn is the voltage. That means this 4f phi m, that is Weber per second, that means it is the voltage. So as the flux phi varies sinusoidally, form factor of sine wave we know that 1.11. So therefore the RMS value of EMF per turn equals to 1.11 into 4f phi m. Okay, that is equals to 4.44 f phi m. So the RMS value, that means the measured value, the value which can be measured, or the active value of voltage or EMF, that is the RMS value. So RMS value of the induced EMF in the whole primary winding, that is E1, equals to RMS value of EMF per turn into number of turn in the primary winding. So the number of turn in the primary winding, that is N1. So E1, that means the induced EMF in the primary winding, equals to 4.44 F into N1 into phi m. And similarly the RMS induced EMF in the secondary winding, that is E2, can be given as E2 equals to 4.44 F into N2 into phi m. So That is the EMF equation. And now from the previous equation 1 and 2, we can write E1 by N1 equals to E2 by N2 equals to 4.44 F5M. This is called the EMF equation of a transformer which show EMF per number of turns is same both primary and secondary winding. It is possible in case of ideal transformer where the number of turns in the primary winding and secondary winding is always same. So for an ideal transformer on no load, E1 equals to V1 and E2 equals to V2, where V1 is the supply voltage of the primary winding and V2 is the terminal voltage of the secondary winding. So that is the EMF equation, and you can see here that is the relation for the ideal transformer and this relation for a practical transformer. So now the next slide is the voltage transformation ratio. So from the previous slide or as derived above, where K equals to the constant, this constant K is known as voltage transformation ratio. If N2 greater than N1, that is K greater than 1, then the transformer is called the step-up transformer. And if N2 less than N1, that is K less than 1, then the transformer is called step-down transformer. So you can see here this N1. If N1 greater than N2, that means if the primary turns is greater than the secondary turns, then it is the step-down transformer, and if the reverse occur or for vice versa, it is the step-up transformer. You can see here this equation from the previous slide. Okay. That's all for today. Thank you.